Hi, it's Mr. T here. In this video, I'm going to go over the 2022 exam paper for Demonstrate Understanding Bonding Instruction Properties and Energy for Level 2 Chemistry, the NCEA. The paper is Achievement Standard 91164. To get the most benefit out of this, what I suggest you do is you go and follow the link below and in the description of the video, and go to NCEA, print off the copy of the exam, and then have a go at it or follow through as I go through the video. It'll give you an experience that's much similar to what you'll be doing in the exam. What I'm going to do is I'm going to unpack each question and say how I'd answer them and give some hints on different skills you might need to answer them. So good luck. Hey, just before you watch the video of me going through this exam, I take the opportunity to like, share, and click the bells for notification if you want to know about more videos that I will make helping you out with chemistry. I hope that video's been... Hi, it's Mr. T here, and today I'm going to go over the exam from 2022. Specifically, I'm looking at the chemistry paper Achievement Standard 91164, or Chemistry 2.4, which is Demonstrate Understanding of Bonding, Structure, Properties, and Energy Changes. I'm going to just talk through how we might answer these questions. I'll give some details, with some specific details you might need to catch up from your notes or other videos. Okay, let's have a look at the very first question. Now, when you open your paper, really you should go through and check each of the questions and start with one that you're the most comfortable with. In this paper, I'm going to start with question 1. I'm quite comfortable with drawing Lewis structures, shapes, and explaining why molecules have their shape. So, with each question in this paper, they're often going to try and put it into a context. They're very keen on putting questions into contexts, but you have to see behind the context and see what is the actual skill they're asking you to do. And the very first question, the first sentence is refrigerants are compounds that are used for cooling, such as air conditioning units and refrigerators. Some commonly used refrigerants are shown below. Now, if we don't know what the word refrigerant is, or we don't know what the rest of it is, we can just ignore this sentence and just look and it says, draw the Lewis structures. Okay, so here we're going to draw the Lewis structures for each one of these molecules, and then we're going to name the shape. Now, ammonia should be a common Lewis structure we've drawn, and we should remember the following rules. That the first step we always do when drawing Lewis structures is to count the total number of electrons. And in this case, there are 3 electrons from each nitrogen and 1 from each of the hydrogen, which give us 8 electrons in total. We then go and put the electrons between the atoms. So we put the nitrogen in the middle and 3 hydrogens around the outside, and we put our pairs of electrons between each nitrogen and hydrogen. We represent that as just a line. And then we have used up 6 of the electrons, and we put the rest just sitting at the top. So this should be like the basic type. We should be happy with this first one. This is the Lewis structure for our ammonia, and then we have to name the shape. We remember when naming the shape, we're not looking at how it looks in our Lewis diagram. We're really counting the total number of bonding and non-bonding regions around the central atom. So there are 4 regions in total around the central atom, which means it's a base shape of tetrahedral. 3 of the regions are bonding, so it's going to be a trigonal pyramid shape. When we come to carbon dioxide, if you've actually practiced this enough, you'll remember that there is a peculiarity about it in that there's some double bonds there. So when we count the electrons for a start, and you count 4 electrons from each carbon and 6 from each oxygen, which gives us a total of 16, in order to have the correct number of electrons around our central carbon atom, we actually have to form double bonds. So here I've formed the double bonds, and remember each one of these lines, these bonds, represents 2 electrons. So if I check this Lewis structure, I have 8 electrons around the oxygen, because I have 2 from this bond, 2 from this bond, and 2 lone pairs, 8 electrons. There are 8 electrons around the carbon, 2, 4, 6, 8, and there are 8 around this. So this is the correct structure. The shape of this, since they're around the central atom, there are only two regions that push against each other as much as possible. They give maximum repulsion. We're going to get angles of 180 degrees, and we're going to produce a linear shape. Okay, so the last one is less common when we draw them, but when we take a nitrogen atom, we have 5 electrons, and there are 2 of them, so there are 10. Now, there is not a central atom, so we'll just draw a nitrogen on either side. And in order to get the 10 electrons for them to fulfill the requirements of giving each nitrogen 8 electrons each, we have to put 6 of the electrons, or 3 bonds in between. So if you look at each nitrogen here in this molecule, we have 2 electrons here, plus 4, plus 6, plus 8, and 2 here, plus 4, plus 6, plus 8. Notice this is a triple bond in the middle. Now, because there are just 2 atoms here, the only shape you can have with 2 atoms joined together is a linear shape. Now, in this case, when they go to mark this, what they're going to do is, sometimes they give you a merit for this question, but in this paper they just gave an achieved. So if you got all the Lewis structures, or you got all the shapes correctly, they gave you an achieved point. Okay, so when we get to the next question, and they're talking about chlorofluorocarbons, CFCs here, they were used as refrigerants in the 70s and 80s, used for hairspray as well. One such example is trichlorofluoromethane. Okay, so that's a carbon with 3 chlorines and 1 fluorine around it, commonly referred to as Freon 11. It's in the table here, and then they've shown another refrigerant, which is sulfur dioxide, which is a chemical that often comes out of volcanoes when we have volcanic eruptions. Okay, so they've told us the name of these 2 molecules, and they've given us bond angles. Notice the bond angle here, 109.5. We should be familiar, that's a bond angle for a tetrahedral shape, and this angle here of 120 we should know is a bond angle for a trigonal planar. We want to compare and contrast the shapes. Now, how I would approach this is I would take one molecule at a time and explain its shape, and then I would explain the shape of the other one, and then just do a quick summary paragraph, sentence probably. So when I do this, I have this acronym I remember, which is SARASBO, which means I need to put down each of these 7 ideas in my paragraph. I have to mention the central atom and their electron density regions around it, that they repel against each other and produce angles in a base shape that will be dependent on how many regions there are. I need to say at the end how many of the regions are bonding, how many are non-bonding, and then say what the overall shape. Let's give it an example. So we'll look at this very first one. The first thing we can say is there are 1, 2, 3, 4. The 4 lines are the bonding regions, and so therefore there are 4 electron density regions around the central carbon atom. In Freon, the carbon atom has 4 regions of electron density around it. Try and use the word electron density. It's a good word to use to explain both bonding and non-bonding electrons. These regions repel as far as possible, or you could say repel for maximum separation, producing angles of 109.5. Now, often we can just say 109 approximate, that's fine, but they'd given us the angle here, so we just write it down. The base shape they make here, 4 regions pushing against each other, is a tetrahedral base shape. You need to remember your base shape. So if you've got 2 regions pushing apart from each other, that's a linear base shape. If you have 3, it's trigonal planar, and if you have 4, it's tetrahedral. So the next part we're up to here, we've talked about the angle and the base shape, is we're going to talk about how many bonding regions. And this one, it's quite straightforward. Around the carbon, all of the regions are bonding. I could say all 4 regions around the carbon atom are bonding, so the overall shape is tetrahedral. So it has a base shape of tetrahedral, but it's also got an overall shape of tetrahedral. Let's explain the sulfur dioxide. So the sulfur dioxide is slightly different. It's the central atom of sulfur, and it has 1, 2, 3 regions. Now notice you have a double bond, a non-bonding pair, and a single bond around the sulfur, but they are all counted as equal when they push against each other. They are all equally an electron density region. So we say in sulfur dioxide, the atom has 3 electron density regions around it. The sulfur atom does. The next thing we're going to say, right, we've talked about that, is we're going to state again they push against each other for maximum separation. They produce angles of 120 and a base shape of trigonal planar. We can see here that it's a wee bit different at the end. 2 of the regions are bonding and 1 is non-bonding. So we write that down and we state its overall shape, which is bent. 2 of the 3 regions around the sulfur atom are bonding, so its overall shape is bent. Let's go back and see what they asked us to do. Compare and contrast the shape and bond angles. So we've done that by just doing these 2 separate paragraphs. We could just round this up and say, oh, okay, therefore that, I guess the summary here would be the angles for Freon are 109 degrees because it has 4 electron density regions around the central atom, whereas sulfur dioxide has 3 electron density regions producing a 120 degree angle. Okay, so they're going to mark this as achieved, merit, and excellence. If you can identify the number of bonding regions or non-bonding regions for one molecule, they'll give you achieved. If you can talk about the maximum separation, these regions pushing away from each other for maximum separation, that's also an achieve point. So that's 2 separate achieve points. For merit, you have to actually explain one of these molecules correctly, and for excellence, you have to explain both. So, 1 second. Let's go to the next part. I've already just filled it in. I pressed the wrong button here. So the next question is, Freon 11 works as a refrigerant in a refrigerator by evaporating, and it's shown below. So this is the equation for this molecule here. So it's just been condensed. It's got an arrow showing it goes from Freon in liquid form. Remember the brackets here with an Ln mean it's liquid, and it goes to a gas. And this is how much energy, this is the energy change or the enthalpy change when it undergoes that reaction. Now, because this enthalpy change is positive, that means this is endothermic. And that means that the particles have gained energy. So we will draw a line at the bottom with our reactants and a line further on at the top with our products. We're going to join them together. Now, whenever we draw a diagram for just a state change, that is going from a liquid to a gas or a solid to a liquid or a liquid to a solid, we don't need to draw the activation energy. There is essentially no activation energy. So you notice I haven't got it in here. The last part I need to draw on this graph here is I need to draw the value of the enthalpy change, or delta RH. And here I've put an arrow, double-ended arrow from a dotted line that is the same horizontal level as the reactants all the way up to the product. So this is the amount of energy that was absorbed in this reaction. So this is a merit question. To get the achieved, you have to have the diagram with all 3 labels. And merit, you have to have the diagram correct. Okay, last one. By referring to both the change in enthalpy and the attractive forces between Freon, explain how this process can be used. Okay, so one of the fundamental things about enthalpy change is when you break a bond, when you break bonds, you are absorbing energy. Okay, and when you form bonds, you're producing energy. So you're giving energy out. So in this case, the difference between a liquid and a gas is the gas has no bonds between it, but a liquid does have intermolecular bonding between it. So the change here is you have broken bonds, and because you broke bonds, this is going to absorb energy. So we need to clearly state that. When Freon evaporates, it breaks the intermolecular bonds between the molecules. Statement number 1. So basically, that's going to give you an achieved, or you put this statement down and it's going to give you an achieved. Bond breaking is endothermic, so heat energy is absorbed to break the bonds. So I've got two two different statements down here, achieved for each or a merit with both of them. If we link it to the actual example, they actually gave us an excellence for this by saying that's how it cools the fridge down. So what you've got essentially happening is the liquid, when it goes to a gas, its bonds have been broken. Bond breaking absorbs energy. The energy is absorbed from the food in the fridge, so it cools down. Now, this is an achieved merit excellence question, and when we add up all of these questions, we get this table at the top here. If we get 2 excellences, we end up with an E8 if we've made no mistakes. If we've made a small error, so let's say in our explanation here for our shape, we did a minor error, and that might have been, trying to think about a minor error here. Maybe you omitted saying it was around the central carbon atom or the central sulfur atom in one of them. They would go, well, you shouldn't have done that, but it's only a minor error, so we'll still give you an E7. So it's quite hard to get the E7 or E8. You actually have to be at excellence level in 2 of the parts here. To get a merit, you need to get 3, and I haven't shown the merit excellence points at the bottom here, but you need to get 3 of those, or 2 of them to get an M5. Achieve is just counting up the total number of achieved points. Oh, sorry, here it is here. So yeah, you can imagine to get a merit, you need to get all of the merit points. To get a achieved, it's 4 out of 5 gets you an A4, 3 out of the 5 give you an A3, etc. Now look, getting an excellence here is a totally, I guess, a point that you should be aiming for. This paragraph here, you should really focus on this paragraph and make sure you get the excellence point in that. That is the Sarasbo one. And this one of this excellence point at the end is kind of weird in 2022, in that it actually wasn't very detailed. So I guess you can guarantee you're going to get an M6 here, and you'll get an E7 or E8 as long as you put as much detail as you can in this. Let's look at the second question. And let me just see if I can go to the next slide. Thank you very much. Nope. Okay, question 2. So question 2, if we just scan it, we can see that the start of question 2, part A, has a question where we're going to calculate, well, we're going to do a calculation using the bond enthalpies or bond energies, average bond energies, and there's one that we're going to do about the polarity. So when I answer a polarity question, I use the acronym UBAC to remind me that I need to talk about electronegativity, uneven sharing of electrons, bond dipoles and symmetry, and finally cancelling, non-cancelling of the bond dipoles. So I'll go back to the first question. They're continuing with their theme of the paper about these refrigerants. So they've got carbon tetrachloride here, and the Freon 11, which is that carbon with 3 chlorines and a fluorine here, and they've drawn a reaction. You would expect that the reaction that they draw is going to show all the bonds that are involved, so that we can calculate the bonds that are broken and the bonds that are formed. And we go to our resource sheet that will be given to us when we do our examination, and we find this equation. So we're going to use this equation to produce an algebraic expression that we will then rearrange to find our answer. And here they're saying they want to calculate what the energy is for a carbon-chlorine bond. Now notice there are actually a few carbon-chlorine bonds on the left-hand side and the right-hand side. So we're going to have to put an algebraic expression on in 2 parts of our equation, and it's not a problem. We'll work out how we do that. We're going to systematically go through, identify what bonds are broken, what bonds are formed, produce an equation, and then solve it. So the very first thing I always instruct my students to do is to produce a table, right? So they're going to tally up the bonds broken and the bonds formed, and you want some way to go back and check that you've done everything right, because it's very easy to make a mistake in this calculation. So the very first thing I do is I take the equation and I count how many of each type of bond is broken on the left-hand side, and I do that by just crossing as I count. So 1, 2, 3, 4. So that's 4 carbon chloride bonds. So here, 4 times carbon to chlorine bonds. The energy for one bond is unknown, so I call it X. So the energy of 4 of them is 4X. Then on the left-hand side, I have to break another bond from this HF molecule, hydrogen fluoride. I'm going to cross that out and account for it. So that's one HF bond. That from the table here, I can work it equals 567. So 1 is also equal to 567. So this is all of the bonds have been broken on the left-hand side, so I'm now going to tally them up, and I'm going to get this algebraic terms here. So we've got 567 plus 4x. X is the unknown energy that we need to find out. So now I'm going to go to the other right-hand side of our equation, and I'm going to work out, well, what bonds were formed. So here we have formed 1, 2, 3 carbon to chloride bonds. Okay, and that's the unknown bond, so it's equal to X, and there are 3 of them, so we're going to write 3X. Excuse me. So at this point here, we might realize that we actually didn't break 4 of these carbon chloride bonds. We only broke 1 of them because 3 of them were reformed again, but we can solve our problem that way. But actually, if we do it this way, we're just going to be less likely to make a mistake, so that's fine. We've formed another bond here. This is the carbon fluoride bond. So we're going to account for that. In this table here, we've got the energy of 485. There's 1 of them, so that's 485. And then we form the last bond here between the hydrogen and the chlorine. That value for that bond is 431. So we're going to write that down, and one of those is 431. Now, some other times when you calculate this, the total amount of energy could be 3 or 4 or 2 times what one of them equals. It hasn't happened in this case, but I'm still going to go through doing filling out the table in this way. Right, so I add all of these up and I get the expression at the bottom that 916 plus 3x equals the bond formed. Now I'm going to substitute these expressions into our original equation, and I'm going to substitute the value for delta RH from the original equation up here, minus 23, into the left-hand side into the delta RH of the equation here. So I write the equation in, and I substitute in these 2 terms and this value, and I end up with this equation here. Now all we need to do now is to group like terms. So you have to recognize that the subtract of everything in this brackets means that both of the values in this bracket are negative, right? So it's a minus 3x and a minus 916. So when we group those together and we subtract 3x from 4x, we get just x. When we subtract 916 from positive 567, we get negative 349. Now group the like terms. I'm going to take this negative, I'm going to add 349 to the right and 349 to the left to cancel out 349 on the right, and we get x equal to 328. And that's our answer. So the value for x here is 328 kilojoules per mole. Now, if we want to get an achieved for this question, we actually need to calculate either this term here at the bottom of the bonds broken or this term at the bottom of the bonds formed correctly. If we want to get a merit, we want to have done this process but with a minor error. Now they term a minor error is maybe we miscounted the number of bonds broken up here, so we might have had 3 instead of 4. So that's a minor error, and if everything else was done correctly, then we would get the merit. To get an excellence here, we need to make sure we get the correct answer with the correct units. Okay, so you have to have kilojoules per mole as the correct unit here. If you just put the number, you would limit yourself to a merit. So it's really important to make sure that you put down the units. Okay, let's look at the next question we've got here. So it's a circle the word below that describes the polarity of each molecule. So when we look at each molecule, we see they both have 4 bonding regions around the central atom. So they are a tetrahedral shape. We know that tetrahedral is symmetrical if all of the atoms around are the same. So the carbon tetrachloride here is symmetrical. So no matter what, because there's 4 bonds that are the same, 4 bond dipoles would be the same, this one here is going to be non-polar. And because this shape here has one of the bonds being different, the overall arrangement of the atoms is asymmetrically arranged, so it's going to be polar. So the first one is polar and the second one is non-polar. But you know what, we can answer this after we've explained it as well. So let's go through and explain. So we're going to explain the we're going to explain carbon tetrachlorides because that's going to be more straightforward first, and we're going to make sure we include each of these 5 points. So the first thing is, in carbon tetrachloride, CCl4, the carbon chloride bonds form bond dipoles because the carbon and the chlorine have a different electronegativity and they share the electrons unevenly. So you need to be very clear that you put in the term, you write down that there is a difference in electronegativity and that they share the electrons unevenly, producing a bond dipole. Okay, so I've got those 3 terms, and that's the first 3 parts of my acronym UBAC here. So the next 2 parts is we're going to talk about whether this molecule is symmetrical or asymmetric. Well, because it's tetrahedral and all that bond dipoles are the same, it is going to be symmetric. So the 4 bond dipoles are symmetric, so they cancel out, and the molecule is non-polar. Let's just check we've circled that. We have. So this is our full explanation here. We've talked about the electronegativity, uneven sharing of electrons to produce bond dipoles that are arranged symmetrically, so do cancel out, and it is non-polar because they cancel. So we go through and we do the next one, and we look that it also has bond dipoles, but it's slightly different because there are 2 different types of bonds here. So there are carbon to fluoride as well as carbon to chloride bonds. The bond dipoles produced from the carbon to fluoride bonds are a different strength from those from the carbon to chloride bonds. Therefore, the bond dipoles are different. And because there are different bond dipoles, there is an asymmetric arrangement of these different bond dipoles, and they do not cancel, and the molecule is polar. So you have to be very specific here and say that there are 2 different strength bond dipoles. And because they're arranged in a tetrahedral shape and they're different strengths, they are not going to cancel each other out, okay? Because you have asymmetric arrangement of bond dipoles. Now, this is most probably the hardest type of explanation you will have to do, so you will have to practice this if you want to ensure that you get an excellence for this. Now, in this case, if you can just write down that there is a difference in electronegativity between the carbon and the chlorines producing a bond dipole, that's an achieved point. Or if you can also say, that the bond dipoles are arranged symmetrically, then and cancel out, you get a achieve point. Or you said they're asymmetrically and don't cancel out, that's an achieve point. To get a merit, you need to link the actually just saying that they're symmetrical or non-symmetrical to explain it, but to get the merit you need to link the symmetry to the cancelling out, or the asymmetry to not cancelling out. So to get the excellence here, you really need to pick apart that the carbon chloride bond is a different strength bond dipole than the carbon fluoride, and that's what makes this molecule asymmetric even though it is tetrahedral. So doing both of these well has really got you to the point where you're guaranteed to get an excellence in this question. Let's move on. So the second question has a couple of extra points here. The part B here is they've given us another what would I say, equation here, and the equation is talking about what Freon does when it's in the ozone layer, which is a layer of the atmosphere, a higher up layer above the troposphere. So what it does is it facilitates or helps the ozone break back down into oxygen, and the ozone is a protective layer. Now all of that stuff there is very interesting, but it actually isn't important to the question. What's important to the question is they've given us this equation with these two molecules, O3, ozone, that's a gas, and O2, that is a gas. And they've given us an energy here value for the enthalpy change in this reaction. And now what we have to do is we have to calculate the amount of energy released when they give us a certain amount of ozone. So essentially what we're going to do is we are going to use a couple of equations. The first one we're going to use is we're going to use the moles equals mass over molar mass equation. And so we go and find that equation. This is in our equation sheet, and because they've given us a mass, and at the bottom we can see a molar mass for ozone, the first thing we're just going to hone in and we're going to solve this, because if we solve part of this, they're going to give us an achieve point straight away. So we're going to put the mass in here, which is 126 over the molar mass 48, and we work out that what's reacting here is 2.625 moles. Now if we want to work out the amount of energy, we have to realize when we look at this equation that ozone 2 moles gives us this amount of energy. So 2.625 is going to give us a little bit more. And how we work that out is we work out that the total amount of energy, Q, is equal to the amount of energy given in the reaction divided by the coefficient. Now the reason for the coefficient is because they've told us that 2 moles give us a certain amount, but we want to know how many moles, so how much energy is produced by 2.625 moles. So if we can remember this equation, this isn't given to us, but it's very helpful. The amount of energy produced equals the energy for the reaction divided by the coefficient of the molecule we're talking about, in this case it's ozone, times the total amount of moles we have. We put those into the equation, so that's negative 285 divided by 2, which is the coefficient in front of the ozone in the equation here, multiplied by how many moles we have, and we work out we have negative 374 kilojoules. Now this is what we would have expected when we talked about it initially. We've got more than the 2 moles it says in the equation, so we think we're going to get slightly more energy. So 374 is quite a good answer, and I'm quite happy with that. And this question, it's only a merit question. They will give you an achieved if you do part of the question correctly. So if you didn't calculate the moles correctly and you put the wrong moles into the second equation, you would get an achieved. Or if you calculated the moles correctly but you didn't do the second equation correctly, you would get an achieved. Let's look at the final question, part of this question 3. So again, they're sticking with this context, this theme. Here is another modern refrigerant, which is also, I guess, a greenhouse gas. Oh no, it says it doesn't act as a greenhouse gas. Well, that's nice. So compound A, we have to identify, is it ionic, molecular, metallic, or covalent? Now the general rule I always tell the students in my class is you look at the periodic table, you look at the atoms involved. If you have only metal atoms, it's metallic. Well, there are no metal atoms in this molecule. If you have metal atoms and non-metal atoms, it's going to be ionic. Well, there's no metal atoms, so it's not going to be ionic. If you have only non-metal atoms, it's going to be molecular. It's only going to be covalent network if it's silicon dioxide, SiO2, or carbon. Every other one we're going to call molecular. So this is going to be a molecular solid. Now, it says here refrigerants need to evaporate to a gas at room temperature to be effective. Use your knowledge of structure and bonding to explain why compound A will evaporate at room temperature. Well, it's molecular, which means it's made up of molecules that have weak intermolecular attractions to each other. Therefore, we're going to start with that, right? So it has weak intermolecular attractions. It's a molecular solid with molecular molecules as particles. So compound A is a molecular solid that is held together by weak intermolecular attractions between molecules. That's the achieve part. We always start with a sentence that explains the structure of our solid we're going to be talking about. Now, why does it have a low melting point? Why does it evaporate to a gas? It evaporates to a gas because it has a low boiling point. Why does it have a low boiling point? Well, weak interactions means a small amount of energy, therefore it has a low boiling point. So when we're talking about boiling points or melting points, that's evaporation or melting or boiling or any of those things, we're talking about the amount of energy required to break the bonds. And that's really important. We link it to energy. Never say force for this one. So because the weak intermolecular attractions, only a small amount of energy is needed to break them, therefore it has a low boiling point. So that's really the crux of how we get the merit for this. This is not an excellence question. It could if it was a comparative question. So if they compared this molecule against another molecule, then we start to get into the realms of it being an excellence question. So this is the end of this part 2, question part 2. And we just count up how many we got right. So as we saw in part A, there were 2 excellence opportunities. So if we got that, we got the E8 already. But if we didn't get the excellence in those 2, we're counting the total number of merits we have to work out whether we get an M5 or an M6. And if we didn't get our merits, 3 merits, we calculate how many A's we got to get the appropriate achieved grade. Okay, let's look at the third and final question. So, okay, third and final question. We're going straight into this similar type of question that we just had. It's just a different variety. They're always going to give us a table like this. And again, I'm just going to go over what I said in the previous question, which is we need to look at each of these compounds here or elements, and we need to identify, do they have metals or non-metals in them? So this first one only has non-metals. It's not carbon, it's not silicon dioxide, so it's going to be molecular. We need to remember that molecular is made up of molecules. That's nice and easy. The attractive forces between the molecules, weak intermolecular attractions. Okay, so notice molecular, intermolecular attractions. Nice and simple. Diamond, carbon solid here. So this, or silicon dioxide, is the exception, and this is going to be extended covalent. Type of particle, always atoms, and attractive forces are covalent bonds because it's extended covalent. Last one, lithium bromine, lithium bromide. We look at these atoms that make it up on the periodic table. We find out that lithium is right on the left, so it's a metal, and bromine is on the right, so it's a non-metal. A metal and a non-metal makes an ionic compound. Ionic compounds have ions, and they have ionic bonds. Awesome. So if we get 2 of these rows or columns correct, they give it us an achieve. If we get it all correct, that's a merit. So we just really need to hold down and learn those rules about how we identify whether the molecules are molecular, extended covalent, ionic, and then learn just the patterns that ionic have ions on ionic bonds, metallic have metal atoms, their localized electrons and metal bonds, and we'll be able to do these tables quite well. Okay, so they're going to choose one of these compounds, or one of these atoms from here and give us a property of it, and we have to explain it. In this case, they're going to talk about carbon, okay, and they're actually going to say it can form as graphite or diamond. Now, you should have looked at graphite as an exception because it is an extended covalent compound, but, I mean, not compound, it's just an extended covalent solid, but it is slightly different because it conducts electricity, and we should be able to explain the reason for that. So diamond is, when we explain diamond or we explain graphite, we're going to use the information we have in the table. That is, we're going to say it's an extended covalent compound that's made of atoms with strong covalent bonds between them. But specifically for diamond, you have first thing we're going to say, they're both covalent solids, but we're going to say that it is covalently bonded to 4 other carbon atoms in a regular 3-dimensional lattice. Now, the reason we've put 3-dimensional lattice, which we should do, is because specifically it's important for this question because graphite is a 2-dimensional lattice. Now, because it's there are no free charge particles, it will not conduct electricity. So this is quite straightforward. carbon atoms covalently bonded to other carbon atoms, 4 of them, in a 3D lattice. No free electrons, no free ions. It will not conduct electricity. So now we go and talk about graphite. Now graphite is an exception. It's a two-dimensional layer or two-dimensional lattice where each carbon atom is covalently bonded to 3 other carbon atoms. That means that one of the electrons is not used in bonding, and that's going to give it free electrons. We'll go over that in a second. But bonded to 3 other carbon atoms, you can say it's in a hexagon structure or honeycomb structure. Most people know that honeycomb is a hexagon structure. The 4th electron from each carbon that was not used in the bonding is delocalized. They are free to move, so will conduct electricity. So because we talked about 2 different things in this one answer here, this is going to be an excellence answer. And if we if we can just identify that the graphite has free electrons, that's an achieved point. Okay. If you can identify that it's the electrons that are going to make it conduct achieve point, if you link that there are electrons in graphite and these are used to conduct electricity, that's a merit. If you can explain both of these points as I've written down here, that's excellence. Often they'll put 2 or 3 of these in a paper, and sometimes they put them in the same question, but they haven't in this paper. They've kind of sprinkled them about, one in last one, one in this one. And remember, you get an excellence for this if you're going to have to compare or talk about 2 different ones at one time. You just get a merit if you're just explaining one of them. Okay, so the last question of the paper here is we've got sodium lithium bromide, readily dissolves in water, as in the equation below. Classify this process as endothermic or exothermic. Well, we should know that if we look at delta RH, this value here, whether it's positive or negative, will give us the indication whether it's exothermic or endothermic. Negative is exothermic because this reaction is losing energy because it gave out heat energy. So this is exothermic because it is negative. The negative value, negative change in delta RH means the reaction releases heat energy. All right. So the next thing is here, it said here's an equation for the, we had this equation at the top for lithium bromide. It will dissolve into lithium ions and bromide ions, and it will give out that much energy. But potassium bromide will dissolve into potassium ions and bromide ions, and it will absorb energy. Okay, so one is exothermic, one is endothermic. So if we dissolved both of them in 200 mils of water in separate beakers, 20 grams of lithium bromide is dissolved on the first, resulting in the energy change. Calculate the mass of potassium bromide that would need to be dissolved in the second beaker to have the same amount of energy. Okay, so this is 2 parts to this question. Let's just answer the first part, this first paragraph first. Let's take 20 grams of lithium bromide. This is the equation at the top, and we're going to work out how much energy. So this is going to involve us using this equation here. Okay, Q equals delta RH. It's not given to us, so we have to remember it, coefficient over N. But the first equation is we're going to work out how many moles of lithium bromide is 20 grams. Now, we're going to be on the right track if they've given us the molar mass for this. And they have. It's 86.8. So we know there's 20 grams, 86.8 grams per mole. We're going to do that calculation. And we know by doing one step, we've already got the achieve point. Excellent. But we want to know how much energy there was by doing this. So we're going to use the second equation, Q, the energy, equals the energy of the reaction, enthalpy of the reaction, over the coefficient, which for this lithium bromide, there is a 1 in front. So we just have a 1 on the bottom, and we're going to multiply it by the moles. So we're going to do this equation here, and we end up that for this reaction, we're going to have minus 11.24 kilojoules of energy. That's excellent. We've kind of solved the first part, but it said, what is the mass of potassium bromide? That's this one here, that has the same amount of energy. So we can't calculate the mass directly. So what we're saying is we know what Q is, we know what delta RH is, we know what the coefficient is, we can find out the moles. So if we find out the moles, we can then go forward and find out the mass. So I'm going to fill in this equation. So from this potassium bromide dissolving into potassium ions and bromide ions, the delta RH for this is 19.9. The coefficient for potassium bromide is 1. Because it's an equal amount of energy they're asking us about, then Q must equal 11.24. Now I'm not making it negative because it said of equal magnitude. That means equal size. That means they're not interested about whether it's negative or positive. They just want the same size number. And notice when I put these into this equation, I need to find out the moles, or I don't know the moles. And if I find out the moles, I can use the molar mass to find out the mass. So I'll find out this answer here. The moles are 0.565. And now I'm going to take this, I'm going to put it into this original equation that's been rearranged. So I want to know the mass. So the mass is going to equal the moles times the molar mass. That's the equation rearranged. I'm going to put in this value of moles, this molar mass from up here, and I'm going to get this answer. Now this is quite a detailed or an intricate sort of calculations, right? There's quite a few steps. So you're going to expect this to be an excellence, which it is. In this one, they want to make sure, and they're targeting this one as 3 significant figures. Remember, we're going to try and do 3 significant figures for every single numerical answer we give, because that's what they expect. And for some of them, you won't get the excellence if you don't put the unit and you don't put the significant figures. Now, remember, you're going to get achieved if you get one of these parts right. If you get like the whole of this first part right or the whole of the second part, it would be a merit. Let me just correct change or correct mass from correct energy change. Yeah, so if you do this whole bit right here, or if you got the wrong energy here but you got the right mass, you get the merit. You only get the excellence if you get the overall answer correct and you get the units correct and you get significant figures correct. Okay, last bit here. By considering the enthalpy change of each process, explain the different results in temperature. So going back to these two processes, this is there's a lot of information here, but you just want to highlight this is the first process. This is exothermic. This is the second one, it's endothermic. So if it's exothermic, we said here it releases heat, so the temperature is going to increase. So when lithium bromide dissolves in water, it has a negative delta RH, and it is exothermic, it releases heat, so the temperature will increase. I could have said in here it releases heat. Potassium bromide, on the other hand, absorbs heat, so the temperature is going to decrease because it's sucking the heat around from all of the particles around it, the water particles, so it's going to feel cold, so it decreases the temperature. If you correctly linked exothermic to increase in temperature and endothermic to decrease in temperature, they give you a merit here. If you identify just a temperature change correctly, they give you the achieved. So this is actually quite an easy one to end with. If we look at this, well, we're not ending, we've got the next part here. Let's go on to the next page. Okay, structure of bonding lithium bromide, why it dissolves in water. Oh, another solid question here. So, lithium bromide. First we have to identify, is it covalent, is it extended covalent, is it molecular, is it ionic, or is it metallic? Well, we have a lithium here and bromide. Remember, we talked about that. Metal and a non-metal, it's going to be ionic. We can draw a diagram here and we can explain it. So here's our diagram. Our diagram is of an ionic lattice. I would expect if you drew it on your paper, it would just be in 2D. Now notice the wee water molecules here. The water molecules look like wee Mickey Mouses, yeah, with Mickey Mouse ears. The big circle is the oxygen. It's slightly negative because it's a polar molecule, so we always draw the slightly negative oxygen side around the positive ion, and we draw the slightly positive hydrogen side around the negative ion. Now because of these polar water molecules, you have one side that's slightly negative, it's going to form an attraction to the positive ion, and that attraction here will be as strong or stronger than the attractions that the positive ions have for the negative ions. And that's why they dissolve, because when the water particles surround the ions, they are enticed to join or to attract to the water molecules, because they're just as strong or stronger to the attractions they have already. So we write this down nice and clearly. We say that the ions are held together in a 3D lattice by strong ionic bonds, because it is an ionic substance. Yeah. So we've talked about ionic substance. It's made of ions held together by strong ionic bonds. However, when placed in water, it's a polar solvent. That means it has a positive side and a negative side. The slightly negative oxygen forms attractions to the positive lithium ions, and the slightly positive hydrogen atom attractions to the negative bromide ions. Now, this overall attraction water molecules ions are strong, as strong or stronger than the ionic bonds. This is why it dissolves. So this last statement is really, you have to get a nice tidy way of saying this. I guess this is a nice tidy way. You just say the attractions that the water molecules form to the ions are as strong or stronger than the ionic bonds have. That's why they dissolve. And this is the last one. This is an excellence answer. Now, the reason why this is excellence, even though it's not comparing, is it's quite an in-detailed explanation here. Right, so this one here, maybe the malleability or the brittle one as well, are explanations that we will practice that will often be an excellence one. Now, in this case, you get an achieved if you drew the diagram with the water molecules around, or you identified that there must be attractions between the water and the ions for it to dissolve, right? You get a merit if you link the strengths to the solubility. So you said, hey, water has strong attractions, that's why it's soluble. And you get the excellence if you say, well, the water has strong or stronger attractions than the ions had in their ionic bonds. So you have to actually go back and talk about the original attractions. Now, if we take all of these, this is quite a different, it's a wee bit different, the marking schedule here. You need 3 E's, so that there were, in the previous part of this question, there were 2 other E's. You need 3 of them to get the E8. You need 2 to get the E7. This is a bit more straightforward with the marking, because we just count the total number of times that you've got the E's, instead of just, oh, did you make a small mistake or not, and you go down to an E7. So that's the 3 questions. In this paper in 2022, they really mixed them up. So they've put the solid questions with the energy questions, and they've tried to mix the energy questions up with the structure and with the molecule polarity and structure and shapes. So, I mean, they'll do that sometimes in the exam they'll put them all, the different ones, in separate questions. But if you practice the individual skills and you practice the old papers, you'll get so much better at it and you'll come out with a good result. Anyway, good luck with your exams, and if you want to look at the other videos I've made, I've got one for 2023, and I'm most probably going to write or go over one for 2022. That video has been useful. If you have any questions, don't forget to put that down in the comment. I'll see if I can answer them for you. Don't forget to subscribe if you want to see some other videos that I have made about this, and give it a like if you found it helpful.